Hello my dear students, how are you? My name is Josia Mwakitalima. I'm a chemist teacher, and for today I'm here to share with you some issues or concepts that most likely to be difficult to most of students. And for today we are going to consider on the issues on the topic known as halogens, derivatives of hydrocarbons. And in this topic, we are going to consider the chemical properties of the halogens derivatives of hydrocarbon. And it is a continuation of where we ended. So our subtopic and the issue that we are going to consider in chemical properties is on elimination reactions of halogens derivatives of hydrocarbons, interconvertibility, and reactions with the metal. So these are the three main issues that we are going to consider. And now let us see what are the competences that you will gain from this topic. The competence that you will gain is you will be able to use organic knowledge in solving different environmental problems, and making sure that you will now be having some tools or skills of making the environment to be sustainable for the future use of next generation. Now let us go directly to the first issue, which is the elimination reaction. Elimination reaction in halogens derivatives of hydrocarbons can be classified into two categories. Like in nucleophilic substitution reaction, here in elimination reaction we have the first elimination reaction and second elimination reaction. So can be classified into first order elimination reaction and the second order elimination reaction. So starting with the first order elimination reaction, here we are going to just to consider the mechanism of how does it take place. The first order elimination reaction, this reaction depends on the only one reactant during rate determining step. So the rate here is being determined by the rate constant, then times concentration of alkyl halide. but where in rate determining step. And the elimination reaction in halogens derivatives of hydrocarbon takes place under alcoholic condition of strong alkaline solution. So let us consider how does the mechanism of this elimination reaction or first order elimination reaction. Now let us take, now we have this one is our tertiary alkyl halides, and normally the first elimination reaction takes place in tertiary halogens derivatives of hydrocarbon, alkyl halides. So here the alkyl group that have been attached to carbon carrying the halogens, which is our functional group, we have 3 alkyl group. That's why we call it tertiary Haloalkane. So let us consider now the mechanism. Why do we say it is a first elimination reaction? So the mechanism now is that during the first step, the halogens and the carbon breaks down. When it breaks down, then it releases intermediate carbocation ion. And from there now, since it involves under alcoholic condition, the beta hydrogen from this alkyl halides is also being removed. So what will happen now here, the second step now, is that the beta hydrogen will also break down. This hydroxide ions is being released by under alcoholic, since we have said it is a reaction under alcoholic potassium hydroxide. So the potassium hydroxide, its role is to release hydroxide ions. From there now, here the beta hydrogen, these are the beta hydrogen. So what is happening when alkyl halides, when the halogens was attracting the electron pair towards itself, then the hydrogen carbon bond becomes also weak under alcoholic potassium hydroxide. So what will happen, since carbon is more electronegative than hydrogen, this beta hydrogen will also break down, and after breaking down, it will release, we have CH3, and this carbon here is negative but having hydrogen, and there this carbon is also having positively charged. The hydrogen that have been released here, which means that it will be released as positively charged ions, will combine with the alcoholic condition that have been released from potassium hydroxide to form water molecules. And from there now, the halogens that have been released will combine with our metal, which is potassium, to form another product, which is potassium chloride. From there now, the positive charge and negative charge will combine together and form the double bond between the carbon. So at the end now, the product will be CH2, double bond C, then CH3. So that is the end product now of our reaction. The other product is water, then plus potassium chloride. So this is what we call it elimination reaction. Why? Since it has been involved removing hydrogen and the halogens that are being removed from the molecule. That's why we call it elimination reaction. And we call it first elimination reaction because during transition state, this is the transition state and this is the slowest state, but this is the first state. So the equation that determines the rate of reaction is this one, the slowest state. And we see that the slowest state involves only one reactant, which is the alkyl halides. That's why we have written here that the rate of chemical reaction is directly proportional to the concentration of only one reactant. That is the first order elimination reaction. Now, if we consider now the second order elimination reaction here, it is denoted E, then 2 there. Second order elimination reaction. This one, the rate of reaction depends on the concentration of 2 reactants. And these reactants are the base, which is the hydroxide ions that are being released by potassium hydroxide, and the concentration of the alkyl halide. So we have the concentration of alkyl halide and times the concentration of a base. And this is why we call second elimination reaction. So during transition state, both the reactants are involved different from what we have observed in first order elimination reaction. So the second order elimination reaction is common in primary haloalkane. You may be asked, why is it common in primary haloalkane? This is because in primary haloalkane there is very, very weak steric hindrance that can be found in that molecule. Why? Because of the absence of the alkyl group that are being attached to our alpha carbon. And as what we have said, the rate of reaction depends on the concentration of the 2 reactants. So let us consider now an example. This is our primary haloalkane because we have only one alkyl group that which is attached to alpha carbon. And then now, if now we react it with alcoholic potassium hydroxide, as usual the mechanism is that during the transition state, the base, an ion which is being released by potassium hydroxide, will go and attack the beta hydrogen, which means that you will have, so this is what we call it transition state, and this reaction is slow. So what will happen now next is that the hydrogen carbon bond now will break down to release water molecules, and the halogens also will break down, and that halogen will combine with the potassium to form potassium chloride. Therefore, from there now the reaction becomes fast, whereby you will end up getting C hydrogen, and there we have another carbon that which have attained negative charge, positive charge, but this one is negative charge, and there we have hydrogen. So the positive charge, negative charge, that means electrophile, nucleophile will fuse together and form another bond. So you'll end up getting the CH2 double bond CH2, then the other product will be water molecule, then plus potassium chloride. So that is the end of the second order elimination reaction. That is what is happening in haloalkane. And here the products formed depends on the natural structure of our haloalkane. Consider the haloalkane CH3, CH2, CH, CH3. Here we have bromine, which is our halogens. Now from this one, if treated with alcoholic potassium hydroxide, so this kind of haloalkane will give up two products, and the two products, one of the product will have the double bond between this carbon and this carbon, because here we have alpha carbon and the beta carbon, and also in this side you have this is alpha carbon and this is beta carbon. So we have two beta carbons, which is one of this carbon and the other of this carbon. So the resulting product or the resulting alkene will have the double bond on the two carbons here. So the first product will be CH3, CH2, CH, then you will have the double bond at this carbon. And the second product will be CH3, CH, double bond CH, then CH3. So these are the two products. And now this one is known as but-1 in, and this one is known as but-2 in. Now of the two products, this but-1 in is the minor product, and this but-2 in is the major product. And this one is in according to Sayzeff's rule. So this is according to Sayzeff's rule, which states that the alkene that have substituted with the most alkyl group from the carbon carrying the double bond is the major product, while the one which is less substituted to the carbon double bond is the minor product. And also if you refer to the positive inductive effect, that means the alkyl group on the carbon carrying the double bond releases electrons by positive inductive effect, thereby strengthening the products or stabilizing the products. So that is according to Sayzeff's rule. So let us now consider another chemical properties, which is the reaction with metal. The reaction of haloalkane with metal, first you are going to consider the reaction with magnesium, and the second you are going to consider the reaction with the sodium. So starting with the magnesium, taking an example of this haloalkane CH3, CH2, then chlorine. When treated with the magnesium, the product formed is what we call it the Grignard reagent. So this is Grignard reagent. And this Grignard reagent is very, very important in preparation of other organic compounds. So that is the main application of Grignard reagent. But the second reaction of haloalkane with metal is the reaction with sodium. The reaction of haloalkane with the sodium takes place under a condition of dry ether. So the condition for this reaction, there must be a presence of dry ether. And it is also known as Wool's synthesis. So the reaction is also called Wool's synthesis. And this reaction doubles the number of carbon atoms for the product to be formed, which means that it is the main reaction that have been applied in preparation of alkane, and it doubles the number of carbon atoms, which means that it increases the number of carbon atoms in the preparation of that compound. So let us take an example. If you have CH3, CH2, CH2, then you have iodine, then treating with sodium. But you have said that the condition is in dry ether. In dry ether, so we have our reactant or our haloalkane have 1, 2, 3 carbon atoms. So since we have said it doubles the number of carbon atoms, then the product will have 6 carbon atoms. That will be the alkane. And the other product now will be sodium iodide. So that is the reaction of sodium with haloalkane in a condition of dry ether. But if the reaction involves the allyl halogen, that means the halogens being attached to benzene ring, is known as fitting reaction. So we have fitting reaction. Fittings reaction. This reaction involves the use of the halogens derivatives when it is a benzene ring. So consider now the chlorobenzene when treated with the sodium. But a condition you have said must be dry ether. Then the product, the benzene ring, will double. So you'll have diphenyl. That will be our product. And the other product will be sodium chloride. So this now, when balancing, this will be 2, here will be 2, and there will be 2. So that is fittings reaction. But if it is a combination of fittings and Wool's reaction, we call it Wool's fittings reaction. So we have Wool's fitting reaction. Wool's fitting reaction, it means that it involves the halobenzene and the haloalkane, but both being treated in presence or in a condition which is dry ether. So here, if you have taking an example of benzene now here, ring with chlorine or chlorobenzene, being treated now with, let's say it is CH3 chlorine, then with sodium, but condition is dry ether. So this is ooze. So this is ooze and this is fitting. So combining them, then you have ooze fitting reaction. So here the product will be CH3, then the other product will be sodium chloride. Then what remains now is the balancing of the equation. Here will be 2 and also here will be 2. So we have 2 sodium, 2 chlorine and benzene there. Here will be 2 and also here will be 2. So that is the reaction that will now be considered as our product. So this is what we call it ooze fittings reaction. The interconvertibility reaction refers to conversion of alkane, alkenes and alkyne into haloalkane. But also haloalkane can be converted into those reactants, which means that this involves alkane, alkene and the alkyne. They can be used to produce haloalkane. But at the same time, haloalkane can be used to produce alkane, alkene and alkyne. That is what we call it interconvertibility. So now let us see how alkane can form haloalkane and how alkene can form haloalkane and how alkyne can form haloalkane. Now let us start with the alkane to haloalkane. Taking an example of CH4, which is methane, is our alkane. This one can be converted into CH3, let's say chlorine. Under what condition? This is when this one, CH4, which is our alkane, is treated with chlorine gas under UV light. This is known as free radical substitution reaction. So here you end up getting CH3, then chlorine. Now this is our haloalkane. But this haloalkane can also be treated to form the alkane, by which now haloalkane to alkane. So this haloalkane, which is CH3 chlorine, this can be treated with by reduction with zinc metal. Then you'll have the product that will be, it is a reduction, which means that plus zinc couple, zinc copper couple, then heated, you'll have the alkane will be the product. So you have converted haloalkane to alkane and the alkane to haloalkane. So it is interconvertibility. And the second reaction is that you can convert alkene into haloalkane and the haloalkane into alkene. So we have alkene to alkane and the haloalkane to alkene. Taking an example of CH2 double bond, CH2. This is our alkene. When treated with hydrogen bromide, you will end up getting CH3, CH2, bromine. Now this is our haloalkane. So if this is our haloalkane, you can do any reduction method to this product by either reduction with the zinc couple with copper, by this is reduction, then you will end up getting also alkene. Or if not that, you can treat this one under alcoholic potassium hydroxide, you will also get up the alkene. So this is the interconversion between alkene to haloalkane. But you have the last one, which is alkyne to haloalkane. And also haloalkane can be converted into alkyne. So take this example, CH3, CH, triple bond, CH is alkyne. This one can be converted into haloalkane when treated with the hydrogen bromide. Under a condition, now you'll have CH2 bromine and the CH2 bromine. This is our haloalkane and it is known as vicinal compound. But you can also change the haloalkane obtained to alkyne by treating it with alcoholic potassium hydroxide and followed by sodium what? Sodium amide, and get the alkyne. So this is what we call it intercompatibility reaction. So this is all about the chemical properties of haloalkane that remained for the chemical properties of haloalkane to be discussed all. So now, after a short break, we'll be back to consider some examples of questions that can be, you can use the knowledge that you have obtained here to answer those questions, and those questions might appear in your exam. So take care. See you later. Okay, welcome back, my students, for doing some sample questions which are concerned with the knowledge that you have discussed here. And the first question is that a haloalkane W with the molecular formula C5 hydrogen 11 and 1 chlorine reacts with aqueous sodium hydroxide to give X which is C5H11 12 and 1 oxygen. But that X reacts with the concentrated sulfuric acid at 170 degrees centigrade to form Y, which is C5H10, which will decolorize. So this Y can decolorize bromine water. And Y also reacts with ozone followed by hydrolysis in the presence of zinc to give methanol and a branched aldehyde Z, which have a molecular formula of C4H8 and 1 oxygen. Now the question that we have been asked is, what is the structural formula of Z, Y, X, and W? But also give the balanced equations for all the reactions involved. So as what we have discussed here, if we consider our compound is C5H11 and 1 chlorine, so it is haloalkane. So if it is haloalkane, we are told that when treated with this to give this one, then here oxygen have been added, but it is aqueous solution, not under alcoholic condition. If it is an aqueous solution, that means probably X will be an alcohol. And if it is an alcohol, then it reacts with concentrated sulfuric acid, which is a drying agent at that temperature to form Y. So Y might be our alkene. And the alkene is the organic compound that can decolorize bromine water. And Y reacts with ozone followed by hydrolysis in the presence of zinc to give methanol and the branched aldehyde Z with the molecular form of this one. So here is where now we can start answering our question, because the product of ozonolysis, one of the application of ozonolysis reaction is in determination of the molecular structure of the alkene by using the product of ozonolysis. So now we have told that ozonolysis yield methana and branched aldehyde. So by considering now the reactions, we have W, which have a molecular formula C5H11, then chlorine. This one reacts with aqueous sodium hydroxide. Then the product formed is X. X have the molecular formula of C5, 12 hydrogen and 1 oxygen. But also X reacts with concosulfuric acid. So this X, when treated with concosulfuric acid, produces what? Y, which have C5 hydrogen 10. So C5, then 10 hydrogen. From there now, this Y decolorize bromine water, which means that C5, which is Y, then decolorize bromine water to form then the bromoalkane, and therefore from there this is Y. But ozonolysis of Y gives that product. So if this is Y, C5H10 gives the ozonolysis followed by hydrolysis produces methana. Methana is this one. And a branched aldehyde, which have 4 carbon atoms, 80 hydrogen atoms, and 1 oxygen gas. So it's where now we can start answering our question. So by backward reaction. So if it is a branched aldehyde, it means that due to presence of 4 carbon atoms, it means that there is only one alkyl group which is branched to the longest chain, which must contain 3 carbon atoms. So H C double bond O C H, then this one branched aldehyde, which means that have 3 carbon atoms, and being branched, if being branched, it means that the CH3 is here. So here you'll be having CH3, and here hydrogen, and there double bond oxygen, then hydrogen. So this is a branched aldehyde. So 1, 2, 3, 4, 4 carbon atoms, 3, 3, 6, 7, 8. So we have 8 hydrogen atoms. That corresponds to that molecular formula. And you also have 1 oxygen gas. So to get now the structure of Y, we just join this part. So this is now our structure Z. So this is Z. And the Y will be by joining these two. So here the carbon having double bond with the oxygen are the carbon atoms that had the double bond in alkene. So you just first join those carbon atoms, which means that if this is the carbon atom, and also we have double bond with this carbon atom. But this carbon atom have CH3, have carbon, and this carbon have CH3 and CH3. But this carbon with the double bond from methana have hydrogen, So this is our structure, our structure of alkene that undergo or in which ozonolysis took place. So here now this will be the Y. Now from there, if we go back now, we have Y with this structure. CH2, double bond CH, then CH3, hydrogen, CH3. So this is Y. Now this Y, backward reaction had an alcohol with 5 carbon atoms and 11 hydrogen atoms. So this might be a primary alcohol because of the product obtained here. If it could be a secondary alcohol, you could have 2 products. So it was a primary alcohol that had a functional group at first carbon atom. So which means that this one now will produce our alcohol that will be CH2, then here OH, then you have CH2, then CH with the CH3, then CH3. So this is our alcohol that we had first before reacting with concentrated sulfuric acid. So here now, this is what we call it now is X. Then if it is X, then after the backward reaction from X, which is our alcohol, to haloalkane, you can treat it by reagent, the backward reaction. It means that the OH here was replaced by chlorine atoms. So from there now you come back to CH3, CH, then here we have CH3, then this will give 1, 2, 3, CH2, CH2, then there will be chlorine. So we have 4, 5, 6, 7, then 10. How many carbon atoms is 5 carbon atoms, 11 hydrogen. So if 11 hydrogen, 3, 3, 6, 6, then 10, 11. So the structure now corresponds to the molecular structure that you have been given. So this will be W. From there now we have asked to write the structural formula of Z, Y, X, and W. So this now will be Y is this one, and X is this one, and W is that one. So Z is this one. So I think now by using that knowledge, it is a reaction involving haloalkane. So it's your task now. I want you, from this summary that I did, to give the balanced equation for all the reactions. You will do it on your own time. So let us go to the second example and see how does it employ to use the knowledge of haloalkane to answer it. Let us go to the second example. The second example is that a chloro derivative of hydrocarbon. When we say a chloro derivative of hydrocarbon, it is haloalkane because we have chloro, which is our halogens. J, named by the name J, when treated with zinc copper couple, gives a hydrocarbon with 5 carbon atoms. Then when J is dissolved in ether and treated with sodium, a compound K, which is 2,5,5 tetramethyl hexane, is formed. So you are asked to reduce the formula of compound J. So which is very simple. Where do we start now? We can just start at this point. Remember, when haloalkane are being treated with sodium in dry ether, we said that it produces a product that will double the number of carbon atoms. So what do? You just write the product which is being formed after reaction between sodium and that haloalkane in dry ether. So the product is 2,5,5 tetramethyl hexane. And if we write the structure of this, we have 6 carbon atoms, 1, 2, 3, 4, 5, 6. And the carbon number 2 have alkyl group or methyl group. So here we have methyl group, and here also we have another methyl group. But to carbon number 5 we also have methyl group. So 1, 2, 3, 4, 5. here we have CH3, here we have CH3. So here will be CH3, and there will be hydrogen, 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 and here hydrogen, hydrogen, hydrogen. So this is our product that are being formed after J being treated with sodium in dry ether. So let us now go and consider how was it. Remember that I told you that reaction of haloalkane with sodium doubles the number of carbon atoms, which means that the reactant, our reactant, since our product have how many carbon atoms here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So here it means that this is the center of our reaction. If this is the center, that means it had 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this means that area before reaction with sodium, this was our reactant. So it could be CH3. C, here we have CH3. CH3 iodine, which means that it is our haloalkane. Here we have CH2, then iodine. So this one, when treated with sodium in dry ether, then the product here will double the number of carbon atoms. So here will be 2, then you will have CH3, 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 then CH2 will combine with another which will be CH2, then CH3, CH3. So probably the structure of J is this one. So this is our J. So that is the end of this reaction. So how do you see how the questions come simple after knowing how to go about with these reactions? Now from there, this is about halogens derivatives of hydrocarbon. Let us see some applications of halogens derivatives of hydrocarbons. As I have said that by using this knowledge, you will be able to use the knowledge of organic compounds in solving various environmental problems. And here, the application of halogens derivatives of hydrocarbon is that they are used in refrigerators. In refrigerators, we have these hydrocarbons, mainly chlorofluorocarbons, although nowadays they are being restricted. So we have another substances which are being used due to its negative impacts on the environment. The second application that they are used as propellants in aerosol inhaler for treatment of asthma. But not only that, but they are also used as solvent for other organic compounds. For example, for biologists, I know you, among of you who are listening to me are biologists, they are using chloroform. Chloroform is a reagent which is used in biology practicals. But also not only that, but they are also used in manufacture of plastics. These are plastic materials. These are plastic material because of these chlorofluorocarbons. And a good example is PVC. PVC is polyvinyl chloride, which have this kind of structure. This is known as vinyl chloride. So vinyl chloride can be used in the process known as polymerization to manufacture plastic material and so on. So this is about this subtopic, which is chemical properties of halogens derivatives of hydrocarbon. So from there now, we have some sample questions that I'll leave to you, and you do it on your own time, and after doing it, I will give you my number and submit it to me so that I can see how have you gone about, so that next time then you can do it, or I can do some correction to you. So this is now my end time. Thank you for listening. Keep on following us. Next time we shall meet. Thank you very much. Okay, now our sample question as an assignment is this one, that if 3-bromo 2,3-dimethyl pentane reacts with alcoholic potassium hydroxide 3 structural isomeric alkenes are formed. So the questions asked A is that name the type of reaction that takes place and give the role of the reagent, which is alcoholic potassium hydroxide. And B, one of the reaction products is 2,3 dimethyl pent2-ene. So give the structure of this alkene, which is that one that given, then show the mechanism for its formation. And the next also, you are told that when, this is question number 4 now, when 2-bromo-2-methyl propane reacts with aqueous sodium hydroxide at that temperature, the two products formed are an alcohol and an alkene. So you are asked to give the balanced equations and answer the following questions. One is that explain, A, explain the type of the reaction that leads to the formation of alcohol and give its mechanism for the reaction. Then B, give the name and structural formula for the alcohol that is produced. And C, explain the type of reaction that leads to the formation of the alkene and show the mechanism for that reaction. D, give the name and structural formula of the alkene which is produced. And lastly, what condition will favor the formation of the Roman 1 alcohol, Roman 2 alkene.